Two that we need to consider. Competition at electrolytes. So this is leading into electrolysis of molten salts, of aqueous solutions. Sometimes more than one chemical. So far, we've only looked at molten salts. So there's only two things to consider. When I put water in, i.e. an aqueous solution, we've got four things to consider. Where is water in reference to, in terms of oxidizing strength? Where is water in terms of reducing strength for the components we're looking at? So we need to use the electrochem series to predict what will occur. The strongest oxidizing agent will react at the cathode, so the forward reaction. The strongest reducing agent, right, will react at the anode, right? Strongest is on the bottom left-hand side. The strongest oxidizing agent is on the top of the right-hand side. Remembering that reduction always occurs at the cathode, oxidation always occurs at the anode. Yeah? No exceptions to that. Note how in electrolysis, in most cases, we'll talk about, when we talk about electroplating, we'll talk about when we don't have inert electrodes. But electrodes are mostly inert. So this is the electrolysis of water, right? So we've got some water with a soluble salt. Let's just say sodium chloride. Looking at my electrochemical series, where's my electrochem series? Let's go back. Electrochem series, I don't have it here. I need to put it back in there. Right, electrochem series, right? Here's my electrochemical series. I've got, let's say, sodium chloride. I need to recognize, where's my, I wanted this bit. Where's that? There, I wanted there. I'll get to that later. So I want to figure out which chemical species are present in aqueous sodium chloride. Yeah, George? So we've got sodium ions present. I've got water present. Yeah? Then looking at the other side, I've got chlorine here. And I've got water here. Yeah? Remember too that the electrochemical series is under standard conditions. What are those conditions? Right, so we've got 25 degrees C, 100 kPa, and 1 molar concentrations. Right? So if I change the concentration, we may change the order, and I'll talk about the exception, like one of the exceptions we need to know. So if we look at just the difference between sodium and water, water is a stronger oxidizing agent, so it will preferentially reduce. Reduction occurs at the cathode. So at the cathode, we have the formation of hydrogen occurring. Yeah? And we would also notice that we'd also have a pH increase due to the presence of hydroxide ions being formed at the cathode. At the anode, right, water is a stronger reducing agent than chloride. Water will preferentially oxidize to oxygen and hydrogen ions. So at the anode, we see a pH decrease and the formation of oxygen, as we see here. So we've got a soluble salt, water oxidizes into oxygen gas, and water also reduces and gives us hydrogen gas at the anode is supposed to be positive. Did I have that right? So positive cathode. Yeah, you're right. That should be negative. You're correct. Yeah, the cathode should be negative here. Negative. Yeah. Right. Anode positive, cathode negative should be. Thank you for picking that up. I'll fix up the image. So note the key word is dilute. Yeah? So dilute, less than 1 molar. Oxygen and hydrogen gas will form. Oxygen and hydrogen, yeah, you can. have some mild salt water, invert some beakers or test tubes and collect off the gas. You need to electrolyze. And this is how most hydrogen is formed, actually, is through the electrolysis of water. Yeah? Yeah. Well, think about hydrogen. Hardly any hydrogen is in our atmosphere because it's got such a low density. Any hydrogen in our atmosphere escapes the atmosphere. Yeah? And it's such a small molecule, it's very difficult to store, which is why we don't have hydrogen stores. Yeah? We've got plenty of water. And so if we think about, so I'll pause this just for chemical series. Chlorine and hydrogen are very close. So at higher concentrations of higher concentration of chloride, so at high concentration of chloride ions, water and chloride swap places on the electrochemical series. Yeah? So at standard conditions, dilute, so less than 1 molar, it's in the position as is written. At higher concentrations of chloride ions, they swap positions. And suddenly chloride becomes a stronger reducing agent than water, and that's how we form chlorine gas. Now, looking back down here, let's go back to here, the difference between water and sodium ions is far more significant. So even at high concentrations of sodium ions, water will still preferentially reduce. Both, right? So knowledge of the electrochemical series is that the order in which it appears is under standard conditions, 1 molar concentrations. At higher concentrations, won't necessarily be in this order. A bigger gap, the effect of concentration will be minimal. Yeah? Really small gap, the effect of concentration, particularly for chlorine, is significant. The difference between fluoride and water is much more significant, right? So if we had high concentration of fluoride ions, we couldn't electrolyze that in an aqueous solution. Yeah? But with chloride, yes, we can. Okay. So high concentration of sodium chloride. At the anode, chloride will oxidize to give us chlorine gas. At the cathode, water will reduce, preferentially over sodium ions. Now, that's the only exception you really need to know in terms of that swapping of positions. Yeah. Cool. And one of our reasons for doing this is because we don't, like industrially speaking, we don't have a lot of need for sodium metal. We have an enormous need for chlorine. Yeah? Hydrochloric acid, chlorine-related salts and stuff for pools. It's a really good oxidizing agent. Yeah? So polyvinyl chloride, PVC piping. So chlorine is important in those reactions. So industrially, we need enormous amounts of chlorine. And it doesn't make sense to take molten salt that requires 800 degrees C to then electrolyze it to get our chlorine, when we can do it at room temperature using salt water. Yeah? So much more energy efficient process of producing chlorine. Nothing. It remains in solution. Yeah? Because the water is preferentially reduced, the sodium ions remain in solution. Yes, exactly right. You would get sodium hydroxide. Here we go. Okay. Now, so far, we've only looked at using inert electrodes. Right, so let's consider what may occur if I use a reactive electrode. So let's say I've got a nickel sulfate solution and I've got copper electrodes. So let's work through this together. So I've got 1 molar nickel sulfate solution, right? 1 molar, standard mole concentration. Power supply, anode, cathode, positive anode, negative cathode, nickel sulfate solution. Got my electrochemical series. I'm going to identify which chemical species are present. The chemical species that are present are water and copper from the reactive electrodes, and nickel ions and water in terms of the other side. So one way to do this is the mnemonic device is all possible SORA half. So we're identifying all chemical species present. So I don't have nickel present. That's one important thing to consider. I've got copper electrodes rather than nickel. So it's not a nickel in a nickel 2+ half cell. It's a nickel sulfate solution. So there's sulfate ions there, but nickel ions. But sulfate's not on the electrochemical series. If you were required to do something with the sulfate from an electrochemical point of view, you would be provided with the half equation for that. So I've got nickel, I've got water present, I've got copper, and I've got water. So out of water and copper, right? So this would be at the anode of water and copper, which is the stronger reducing agent? Copper. So we would expect then at the anode that copper would oxidize, yeah? At the cathode, I've got nickel 2+ and water. What's going to happen there? Right. Nickel 2+ is a stronger oxidizing agent, so it will reduce to nickel at the cathode, yeah? So observationally, we would see that at the anode, the copper would be going into solution. We would see that the solution would be going from the greeny colored nickel sulfate to the bluey colored, right? As copper ions are forming into the solution, it would turn more blue and would be less green as nickel begins to deposit at the cathode. Make sense? Okay, now you have a go. Pause that.